Hey, good morning, folks, or good afternoon, good evening, whenever it is you find time to find this, I guess. Welcome to our first Physics 30 video. Okay, so we're going to do a video lesson. We're basically going to pick up right where we left off in Physics 30. Okay, so if you have your Chapter 11 note booklet, that would be on page 9, the ion propulsion question. So we'll start out today finishing that off. Um, this page 9. Okay, if you don't have one, if you left it here, you can grab it, or you never got one to begin with. There'll be one posted on Google Classroom. If you can't print it off from there, then just take some paper and a pencil and just kind of take notes as you go. Okay, um, it's not ideal, but it's not ideal time, so we're gonna do the best we can. Okay. So yeah, let's jump right into it. I'm going to finish up the ion propulsion question to begin with, and then we'll keep working through chapter 11. Okay, so jumping back into this ion propulsion question that we were looking at last week, where we left off, um, just to kind of remind ourselves of what were we doing here. Well, we had this engine that is has we know its mass. Okay, maybe we'll write that in. Mass equals 47.2 kilograms. Okay, and how does this engine work? Well, it takes hydrogen ions, which again is just a proton, right? You think about a hydrogen atom, it's just a proton for the most part. So there's different isotopes, but a simple hydrogen, hydrogen 1, we would say, right? That's all it is. So what do you take away its electron, ionize it? What are you left with? Just a proton, right? So when we say hydrogen ion, we're really talking about a simple proton, okay? Now, anyway, how does this engine work? Well, it has these two electrically charged plates here, right? In other words, these two oppositely charged, I should add, electric plates that between them, then there's an electric field, right? There's also a voltage, a potential difference. Remember, potential difference means per coulomb, how many joules would it take to move a charge through this field, right? To a different point in this field. So that is the voltage. So across this had a voltage of 25 times 10 to the 6 volts, or 25 million volts. What is that saying? It's saying for every coulomb of charge you're going to move, it's going to take 25 million joules of energy. Okay, so remember a proton has a charge of 1.6 times 10 to the negative 19 coulombs. So we're dealing with a very small number of coulombs, right? A high voltage, very small number of coulombs. So uh, that sounds like a huge number, but remember, a very small amount of charge is getting moved. However, protons are also very small, so if we can move a whole bunch of them, we can actually provide a decent amount of thrust for this engine. Okay, let's just think about our electric field here for a second. We have protons, we said, hydrogen ions that are going to be accelerated out the back of the engine like this, right? And so if you're a positive charge, you got to be asking yourself, if you're a positive charge and you're getting accelerated that way, well, then which way is the electric field? How do we define electric field direction? It's what a positive charge would do. So they're going to get basically accelerated that way. Okay. There's actually a little bit of an extra step here. So how do the protons get ionized? Usually by an X-ray or something like that. They get shot through, and then there's actually another piece that will add an electron back on. The reason they do that is so that there's no more electrostatic interactions once the hydrogen's left. Okay, so you're not messing around with stuff that you've already used to propel yourself forward. But that's kind of beyond the scope of what we're talking about here. Let's back it up a bit. Okay, so again, those red lines are our electric field, and we know that because we know the hydrogen ions are going to be propelled that way. That's the way they would move in that field. A little bit of an extension here, that means this plate must be positive charge, and this plate must have a negative charge. Okay. Uh, all right, we'll jump back into our solution. So just to remind ourselves of what we were doing, we needed to find, we need to find the change in energy that this setup here, these two plates with that voltage could provide for a hydrogen ion, okay? To find that, we can use the fact that, well, per coulomb, right, what change in energy can it be provided? That is a potential difference. That's a voltage. So we're looking at now, with this setup, what's the possible energy change that could be provided to a proton, okay? And now, you'll notice if you had our solution followed along, kind of copied up to where we were last week, I've kind of deleted something here. The reason is I made an assumption without saying it, and I really should have said it. What I had before was this. Change in kinetic energy is equal to m times the change in v squared over 2. And I realized I really shouldn't have said that, okay? This is okay, but only if EKI is 0. So we are going to make that assumption, but I should have said that we were making that assumption, right? The reason that doesn't work is, imagine if we took, we're saying any change in EK is equal to m times any change in V squared. So that's what we're saying is EKF minus EKI, right? The final kinetic energy minus the initial kinetic energy. Imagine I had said then mVF squared over 2 minus mVI squared over 2, or 1/2, whichever one you like better, okay? Then what I'm claiming, I'm just going to pull out m over 2 as a common factor. I can do that. And there is where it breaks down, right? The difference of these squares is not the same as the difference. It's only true if you have 0 as your initial. That's the only time I can really say what I said up there. So uh, just as an example, if VF, I'm just going to throw in some example. What if VF was 6 and VI was 4, right? Well, then I have 6 squared minus 4 squared gives me 36 minus 16. Well, that's 20, right? So if what I had said up here were true always without making my assumption that EKI was 0, right? If that were true, then this should be true for anything where my VF and my VI are separated by 2. So what about, I don't know, 12 and 10? Those are separated by 2, right? Should really be putting in units, but just to demonstrate my point here, 12 squared, that's 144, minus 10 squared, that's 100, equals 44. That's not the same number, right? That's not the same number. So this doesn't work. All you need is one example where it doesn't work. So what I wanted to be clear about is that I was making an assumption here that I didn't make super clear that I was making, okay? So we're still going to kind of do the same math in the end, but I should be a little more careful about what I had written down. So I just wanted to fix that. Okay, let's get rid of all this and let's just get back into solving. So ready to do it right this time. We're just going to state our assumption, assuming EKI equals 0, kinetic energy equals 0, which is probably an okay assumption. Yes, they are going to be moving around, but realistically, the energy they're going to gain from being accelerated through this electric field is going to be huge compared to the kinetic energy they have just kind of floating around in there. So I would say this is a fairly safe assumption. EKI is going to be essentially 0 compared to EKF anyway. Okay, so assuming EKI equals 0, well, the change in energy, whatever energy they gained by being accelerated through here, what's going on here? Whatever energy they gained by being accelerated through this electric field that we've drawn up here, right? Well, then that we found with charge times the potential difference, based on the definition of potential difference, where is that energy going to go? Well, assuming the best efficiency we can, then the change in that electric potential energy is going to become kinetic energy. Right? Whatever potential energy they've now lost by being accelerated is going to become kinetic energy. The same way we can think of it as we did with gravity in physics 20, right? If I were to drop something from up high, from a point of high potential energy, it would lose that potential energy, but it would gain kinetic energy on the way down. It'd be moving faster and faster and faster the whole way down, right? It's the same idea here. When these hydrogen ions are here, they have a lot of potential energy because they're in a strong electric field. As they move, they lose that potential energy because they're getting closer to the negative plate, which is the ground in our gravity analogy, right? But they're gaining kinetic energy. They're moving very quickly, faster and faster. So let's just figure out if they lose this much potential energy, electric potential energy, how much kinetic energy are they going to gain? Let's just call it a change in potential. Okay, change in potential equals the change in kinetic. And that now, since we're assuming, will be equal to EKF minus EKI, and we're assuming that they essentially have no kinetic energy initially, which will realistically be a safe assumption because they're going to get a whole bunch more kinetic energy from this electric field than they would just floating around in the engine being ready to be used. Okay, so that means the change in E is equal to EKF, which is equal to mVF squared over 2. Okay, and so this, what were we trying to find? We're trying to find the change in energy it can provide for hydrogen ions. Okay, to get not really the change. I mean, it is the change in V because we are looking for the VF, which if we started at 0, VF is the change in V then, right? So then VF squared equals 2 times the change in EP over the mass, and we'll just square root. Okay, and now we're ready to solve. So the final velocity, which is really the change in V, is going to be equal to 2 times the change in potential that we just calculated using change in E equals Q times V was 4 times 10 to the negative 12 joules. Okay, so 4 times 10 to the negative 12 joules, all divided by the mass of the hydrogen ion, which again is just a proton, so look on the back of your formula sheet for that mass. But soon enough, you'll probably have it memorized once you do enough of these examples with protons. It's 1.67 times 10 to the negative 27 kilograms. Don't forget to square root. Okay, so I'm getting that the V final for a hydrogen ion, okay, is equal to, sorry, this is not the best way to show it, but I got 6.9212, let's go 854 meters per second. Okay, so if it starts from rest, that is the max change in velocity that can be provided. Okay, so now what we were doing before is we said, okay, so that's how fast this engine is capable of making hydrogen ions move. Great. How does that tell us? Because don't forget, what we're trying to do is figure out how many hydrogen ions it would take to make this engine move 1 meter per second faster. So to do that, we need to go back and say, okay, great. So if this engine with that potential difference can make something with that charge move this quickly, right? It's going to make every hydrogen ion move that quickly. Now we're going to say, okay, great. What applies here to make it actually move? Why is it going to move forward? Well, it's going to move forward. Remember, energy is a scalar, so it's not necessarily moving forward as a consequence of the conservation of energy, at least not directly because of the conservation of energy. We need a scalar, right? Or sorry, we need a vector to make it move forward because something else is moving backwards. What vector can we use that will preserve this kind of motion? Well, that's physics principle number 4, the conservation of momentum, right? If suddenly this, whether it was stationary or whether it was moving at some constant v or whatever, even if it wasn't moving at a constant v, if these suddenly now have some momentum backwards that they didn't have a moment ago before being accelerated through the electric field that's in here, right, then that new momentum, quote unquote, new momentum needs to be canceled out by some other new momentum in the other direction, right? Now you take a bunch of tiny, tiny massed hydrogen ions, add them up enough, we can figure out, I should really make that a lot bigger, right? If that's a V vector anyway, okay? So then, sorry, not if that's a V vector, if that's a P vector, if that's a momentum vector, okay? Because all of these blue ones added up should equal this one, equal but opposite direction. Okay, so if all of these hydrogen ions end up going that way, the momentum needs to be canceled going this way. All the momentum initially equals all the momentum finally. And we were kind of saying that in a different way before. We were saying that's another way of saying that the impulse experienced by all of the hydrogen ions will be equal but opposite to the impulse experienced by the engine. So in other words, whatever impulse the hydrogen ions gain to the right, then the engine, must gain to the left to cancel that out, right? And so we know that the change in momentum, the impulse experienced by the hydrogen ions, can be expressed as, yes, Ft, but we can also express it as m times a change in V, right? Or m times Vf minus Vi. So maybe that's for H, of course. MHVIH is equal to negative, in other words, in the other direction, the impulse experienced by the engine. So equals negative the mass of the engine times the change in velocity experienced by the engine. Okay, and these are velocities. Just going through, what do we know? Well, we know the change in V, Vf minus Vi, if Vi is 0, right? We'll assume the engine also needs to start at 0 if the hydrogen ions started at 0, right? They're kind of attached together at the beginning. So the change in V of the engine, also Vf Vi, we know that. We were given that it's 1 meter per second. Okay, we know the mass of the engine. We were given that. if we can figure out the total mass of the hydrogen, right, the total mass of hydrogen required, we know the mass of one hydrogen, so take the total and divide by the mass of one, and that will tell you the number of hydrogen ions possible, or necessary. Okay, so just a quick manipulation here because we want the mass of hydrogen, so we'll just divide by the change in velocity of the hydrogen ions, change in velocity of the hydrogen ions, and so we have now uh, essentially what we're saying here. Remember, always kind of ask your equation, what is it telling you, right? We're saying that the total mass of hydrogen would be equal to, in the opposite direction, the impulse experienced by the engine, right? And then really where we started was that the impulses were equal but opposite, but now we're just saying, okay, if the impulses are equal but opposite, divide by the change in velocity of the hydrogen, and then you'll be left with the total mass of the, should really be labeling hydrogen, right? Hydrogen ions, but I'm not going to put the plus every time, sorry. Okay, so the mass of the hydrogen ions, this is the total mass. So it's the mass of, and it will be way more than I've drawn in my picture here, but right, it's the total mass. Think of this as one object that's now moving that way, right? It's now moving that way so that the engine can move this way. So if we go back, mass of the hydrogen ions is equal to negative the mass of the engine is 47.2 kilograms times the change in velocity of the engine, okay, is 1 meter per second. They just tell us that. However, let's be careful. It's a velocity. It's not a speed, right? We're dealing with physics principle number 4. Momentum is a vector. So let's just slap down a definition of how we are going to define our coordinate system, our directions. So I'm going to say these directions are positive, these directions are negative. The way I've drawn my picture, we would say that the engine is going to the left here, right? So the negative direction, okay? So that means that change in V is going to be negative 1 meter per second, okay? Divided by the change in velocity of the hydrogen. Now we know that's the other way. It's got to be, right? No, using our physics principles. Well then, so this number is positive. So that's 6.9212, positive 6.9212. 854 meters per second. And that, again, that's positive because it's in the other direction. Okay, so if you plug that all in, your negatives will end up canceling each other out, right? Negative, negative is a positive. And so I got that the mass, the total mass of the hydrogen is 6.81954 times 10 to the negative 7 kilograms. So now we're very, very close. We're close to getting our answer right, but it didn't ask what's the total mass of hydrogen ions needed. It said how many hydrogen ions needed. So here we have the total mass of the hydrogen, right? The mass of this bunch of hydrogen ions. If we think of it as one object, that's the mass of this one big object that's really a cluster of hydrogen ions moving to the right. Okay, so what's the mass of, what's the number of hydrogen ions? Well, take the total mass and divide it by the mass of one hydrogen ion. So we will say that the number of hydrogen ions is equal to the total mass, right? mH tot, let's say, divided by the mass of just one hydrogen. So mass of one hydrogen ion. Okay, so this really is the total mass of all hydrogen ions up there, right? And you're kind of used to this sort of calculation. It makes sense if I say, okay, we have 20 cookies in here and every student brought 2 cookies. Well, then how many students are in here? You take 20 divided by 2 and there must be 10 students, right? They all brought 2 cookies, so we have 20 total. Same idea, just with hydrogen ions and the mass of a hydrogen. So the total mass is equal to 6.81954 times 10 to the negative 7 kilograms. Okay, small number, but remember the mass of a hydrogen ion is even smaller. So 1.67, it's just a proton, times 10 to the negative 27 kilograms. Again, that number's on the back of your formula sheet. Okay, so the number of hydrogen ions must be whatever that is, and I'm getting 4.08355 times 10 to the power of 20 hydrogen ions. Okay, but we do need to check our sig digs. That's our raw answer. We'll leave a bunch of sig digs now in case we need them later. But to the 2 sig digs that we were given, because the velocity of the engine, or the change in velocity of the engine, sorry, was 1 meter per second. So the number of hydrogen ions would just be 4.1 times 10 to the 20 ions. Okay, and that would be our answer. For part A. Okay, so for part B, how much work is done on the hydrogen gas? Okay, so how much work is done on the hydrogen gas? Well, as always, work just equals a change in energy, right? That's work energy theorem. So if you look at an object and it seems to have lost energy, work must have been done on it, right? We can't violate the law of conservation of energy. It can't have lost energy, it can't have gained energy. So if it looks like it did, well, something did work on it that we're not thinking about. Okay, so the work equals the change in energy. So what work was done on this object? Well, we can use the fact that EKF minus EKI. Okay, and sorry, I should mention, why am I not just using the same number as before with the one hydrogen ion? Because it's saying how much work is done on all of the hydrogen gas. Okay, so we're going to use the total mass now, the total mass of the hydrogen ions, with the fact that we know the velocity they've gained to get the total change in kinetic energy. Okay, so again, we're making the assumption that kinetic energy initial is equal to 0, and then we have that the work is the change in energy, which is just really the kinetic energy final, right? So mvf squared over 2, which is, again, this is the change in energy just because it started from 0, okay? So the work then is equal to, what is the mass of the hydrogen ions? Well, it would be 1.67 times 10 to the negative 27 kilograms times this number, right? But we already found the total mass. Let's just use that, right? We already found the total mass of hydrogen, 6.81954 times 10 to the negative 7. So 6.81954 times 10 to the power of negative 7 kilograms times their final velocity squared, which we found to be 6.92152.854 times 10 to the 7 meters per second squared, all squared. And that's all over 2. And so I got that the work that happens when the work that is done on the total hydrogen gas, right, all of the ions that are going to get pushed out to provide this 1 meter per second change in velocity for the propulsion engine, 1.6320 times 10 to the 9th power joules, or 1.6 billion joules of work were done on the hydrogen gas. So once again, we'll keep some extra significant digits just in case we need more precision later, but we should, since this is an answer, give it to the appropriate 2. So 1.6 billion joules. Okay. Or 1.6 gigajoules if you prefer. Okay, on to letter C. C asks, how much work is done on the engine? Okay, so if this were a perfectly efficient machine, if the law of conservation of energy was perfectly, well, the law of conservation of energy is always perfect, right? It's just, it doesn't always perfectly transfer from the form you want into the other form you want, okay? So if it were true, or if it were 100% efficient, this would be our answer. So let's find out how efficient this machine is. Is it actually doing that? So the work in the machine, or sorry, in the work done on the engine is the change in energy of the engine, okay? The change in energy from potential to kinetic, let's say, which again is just going to equal the final kinetic minus the initial kinetic. And we're going to assume that it essentially started from 0, okay? And so we have that the work, once again, is equal to the final kinetic energy. Again, really minus initial, but since initial is 0, the total work done will just be equal to the kinetic energy it ends up with. So let's do this for the engine. That equals m engine, V engine final squared over 2, which the mass of the energy is 47.2 kilograms. The final velocity of the engine, as we were told, is 1 meters per second. Square that all over 2, and so the work done on the engine, you can probably already tell where this is going, much, much smaller. Okay, so the work done on the engine is only 23.6 joules. So I can hear you saying already, right? Whoa, that's a very different answer between B and C, and I agree. Okay, but first, before you get ahead of yourself, let's go to D, because D asks, right, exactly what you were about to ask me. To demonstrate your knowledge of the concept of isolated systems while commenting upon the two values of work you just calculated. Okay, well, what do we know? In an isolated system, right, energy and matter cannot escape, right? They can neither enter nor leave. So is this engine an isolated system? If it were, right, then if we imagine the system a moment ago where these were all together, right, where these were still part of the engine, we say, okay, that's going to be our system, right? Then whatever work was done on them needs to be done on the engine, right? Otherwise, energy has left. Something has had its energy changed, and another thing hasn't also had its energy changed. So how could energy have been conserved, right? Whatever work was done on these would have needed to have been done on the engine. So when we go back and we look, okay, if we consider, is that an isolated system? Our hydrogen engine system, is it isolated? Well, you tell me, right? Those would need to be the same value. Okay, so energy is clearly being lost somewhere because all the work done on the hydrogen is not being done on the engine. Okay, so we haven't considered the work being done on something is all that means. Okay, so to comment on it, it's clearly not an isolated system. Okay, because no system at the end of the day is truly isolated unless the system you happen to be talking about is the universe, right? So energy is clearly being lost somewhere. Energy being lost somewhere. Often the answer is heat. Okay, there is also a little bit going on here with the motion of a charged particle and how that interacts with other fields, okay, which we will get to in a bit here in chapter 12 a little bit more. We won't bother too much obsessing about it now. For now, right, what I would like to see from you here is just that you know that if the work done on the hydrogen is not the same as the work done on the engine, clearly it's not an isolated system, right? Because by definition, no energy enters or leaves an isolated system, or matter for that matter. Okay. Um, okay, let's move on to E. What does E ask us? If the two rings are 15 centimeters apart, what is the average force on the hydrogen ions? Okay. Well, two kind of ways you could approach this. You could kind of go in with a Newton's second law, grade 11 approach, right? I could actually give this to my physics 20s if I did it this way. So what I mean by that is, what if we just said F net equals mass times acceleration, right? We know the ion's acceleration because we know their change in velocity, right? And we know their displacement. So let me show you what I mean. We know that F net equals ma, and you might be saying we don't know a, but take a physics 20 approach, right? What do we know? We know VF, right? We know VF, we know VI. Let me just write some of it down actually. So VF is 6.9213 times 10 to the 7 meters per second, right? We know VI we are assuming is 0, or close enough in comparison, okay, that if we were to subtract them, we would basically get the same number. What else do we know? We know the question just told us that the distance between the two plates, the two charged plates, is 15 centimeters, or 0.15 meters. And what are we looking for? We're looking for the acceleration. Okay, so if I'm in physics 20, I'm looking at this and I'm saying, great, I got a VF, a VI, a D, and an A, right? Or so I'm looking for an A. I can use this guy. So VF squared equals VI squared plus 2AD. And hey, my life's even easier because VI is 0. So then 2A, whoops. So then 2AD equals VF squared divided by 2D, and A equals VF squared over 2D. Okay, now we want the force that would cause that acceleration, right? We know all that stuff. So let's take that A, or that expression for A, and go stick it in here. So F net, yes, it equals MA, but A is VF squared over 2D. So the force exerted on the ions while they are accelerated through this field would be the mass of an ion, right? So per ion, this is the force they're going to feel, okay, times their final velocity, which again, 6.9213 meters per second, whoops, times 10 to the power 7 meters per second, going through my purple line there, divided by 2 times the distance they travel, which is 15 centimeters, okay? And so crunch the numbers, you'll get that the force exerted per hydrogen ion is 2.6667 times 10 to the negative 11 newtons. Okay, or to our 2 sig digs, the force exerted per hydrogen ion would be 2.7 times 10 to the negative 11 newtons. Okay, now great, that works, right? If that works for you, that's awesome. Physics 20 doesn't break down just because now we're in physics 30, right? Physics 20 is still there, okay? Let's try another way though. We learned some new equations. Let's take them for a spin. Or we have another option. What if we did it a little more physics 30? Well, we're looking for a force, right? So we have an electric field. We know some stuff about charges. So I'm kind of thinking, what about the electric field is equal to the electric force, the electrostatic force divided by the charge, right? Okay, cool, great. Assuming these are the vectors, I guess I should really let's just say magnitude to keep it safe. Okay, we know the charge. We're looking for the electric force, but we don't know the electric field. However, we do know that the magnitude of the electric field is equal to the potential difference, the voltage, divided by the distance between the plates. So this is the equation for the electric field between two parallel plates, right? So the equation based on the potential difference, and if this is separated by 15 centimeters, right? We can find the strength of that electric field. So there we go. Do we know this? Yeah, they told us at 25 million volts, right? Do we know this? Yep, 15 centimeters. So let's take that expression for the potential, or sorry, for the electric field and plug it in over here. Okay, so then we have that, yes, the electric field is equal to the electrostatic force over the charge, but since this is this, then the potential difference over the change, or the separation distance between two plates is equal to the electric force over the charge, right? Just saying that electric field is this and this, so these are both equal to each other. Essentially what I'm saying is the electric field equals the electric field, which is of course true. Okay, so multiply by Q, multiply by Q, and we get that the force, the electric force will be equal to, the electrostatic force, sorry, will be equal to Q times the potential difference over the separation distance between the two parallel plates, and we got 1.60 times 10 to the negative 19 coulombs. That's the charge of a proton, which is the same thing as a hydrogen ion once again. times the potential difference, which we were told was 25 million volts, 25 times 10 to the 6 volts, or 25 megavolts, whatever floats your boat, okay, divided by 15 centimeters. And so the force, the electrostatic force experienced by each hydrogen ion would be 2.6667 times 10 to the negative 11 newtons, which of course is the same answer we got with our more physics 20-ish approach, right? If we got a different answer, we'd be worried, okay? So if you're sitting on a test, you got a whole bunch of time, you can try it both ways. But realistically, whichever one jumps out to you, whichever one makes the most sense, go ahead, okay? Let's just clean this up. It's a force, so it's a scalar, okay? And I should do this for my other one, but I'll just do it here for now, because it'd be the same thing. Which direction would it be? Well, remember, we weren't told that the engine was oriented left, right, or anything, so all we can really say is towards the negative plate. That's the direction of the force they are feeling, right? And that's a good enough answer. So 2.7 times 10 to the negative 11 towards negative plate. That's what they're feeling while they're between those two plates. Of course, that's also the direction for the other method we use to answer this question, but you've seen it once, you've seen it enough, I would say. Okay. All right, F. Sketch a graph of electric force as a function of time as the particle passes between the two plates. Okay, so interesting. Electric force as a function of time, we'll just go ahead and call it the magnitude, as a function of time, okay, as the particle passes between the two plates. So we're just sketching, so I don't need to be too fancy here, but we got to ask ourselves, anytime we're sketching a graph, right, first things kind of first, where do we start? So when we start, let's, actually I'm just going to draw it so I don't have to keep going up and back and forth, right? If I have my propulsion engine, okay, with the oppositely charged plates, let's do the blue plate is positive, the red plate is negative, okay, so negative, positive. If I'm a hydrogen ion, if I'm a hydrogen ion here, right, as soon as I enter that field, do I feel a force? So once I'm in there, is the force 0 or not 0, right? As you're in this field, yeah, no, you're feeling a force. That's the whole point of a field, right? If a charged particle enters a field, it feels a force. So this is not where we should start, okay? That is wrong, okay? There is some non-zero force. Now, these are two parallel charged plates. So we have to ask ourselves, how does the charge, how does the force experienced by the charge, rather, change as it moves, right? Well, remember, in a parallel plates, that electric field is uniform, right? We kind of talked about that last week, but remember, the farther away you're getting from the positive plate that's pushing you, while the closer you're getting to the negative plate that's pulling you. So kind of the field stays uniform throughout. If the field stays uniform throughout, then the force stays uniform throughout, right? By this, E equals Fe over Q, right? If E isn't changing, that's not a Q. If E isn't changing, the electric field isn't changing, well, the charge can't be changing because that's just a hydrogen ion going through, so how could the force be changing, right? If the force isn't changing, the other thing we can kind of say here, when we did our acceleration, we think about the fact that this might be non-uniform acceleration. No, right? If it's uniform acceleration, the force must be uniform. What does that mean? It means it's not changing over time. So on a graph, right, how would we draw that? There we go. It always feels the same force. While it's between the plates, it's always feeling the same force. Okay. Also notice time didn't pop up anywhere in our equations. We were calculating force and we never had to think about time. Okay. So time is not a factor. Force is not a function of time here. Electric field is definitely not a function of time here. And so it's not changing. Okay. We would say uniform, let's say uniform E, electric field, therefore uniform force. Right? We can go further with that. If uniform force, there's uniform acceleration. Okay, although the question didn't ask about that. Okay, cool. Now, G asks us, derive the equation To determine the electric field between the two plates explicitly using graphical analysis. Okay. Okay, so we want to know what the electric field magnitude, how can we graphically get it? Well, there's kind of two things that it would be, maybe we might think about. What about kq over r squared? That would tell us the magnitude of the electric field. Also, whoops, also the potential difference divided by the distance separating the plates would be useful here too, right? Now, right away, you can kind of think about it. Well, what's Q here? Q is the charge of the source charge, right? This is a point, we generally think of it as our point source electric field equation. So Q, what's the source in a parallel plate problem, right? There's not some necessarily source, at least that we know. We don't know the source of some charge. So that's going to charge of some source. So that's kind of no good to us here. However, this one, that is going to tell us something probably pretty useful, right? So I'm going to actually plot, let's see, the voltage or the potential difference as a function of the separation distance between the plates. Okay, so to think about the relationship between the voltage and the separation distance between the plates, I always, again, find it kind of helpful to think about it in terms of gravity at first, right? So through a gravitational field, again, there's no really perfect analog to voltage, but it would be joules per kilogram, right? We just don't have a name for that, but it would be joules per kilogram. So per kilogram, how much energy would you have to use to lift something through a separation distance of zero? Well, you wouldn't have to do any, right? So in our gravitational field, the whatever gravitational equivalent of voltage, the joules per kilogram, would be zero, right? Now, if we go over to the real thing, right, if we're saying, okay, if we have two plates separated by zero, what's the potential difference between them? Again, zero, right? It would take no work, no energy to move a charge from from a through a plate separation of zero. So we can indeed have our intercept start at zero here. Okay. Now let's just think about what happens as we increase that plate distance. Does it increase square? Does it decrease? Does it decrease? Is there an inverse relationship here, or is there an inverse square relationship here? For that, let's kind of go to an equation. Okay. So we have our electric field equation, right, is a potential difference divided by the separation distance. And so if I solve that for our y variable, this is always what we kind of do in graphical analysis, right? What happens if I double d, right? If I double the separation distance, well, I'm going to double the voltage, right? If I quadruple D, I'm going to quadruple the voltage if I, whatever I want to do, right? Even if I go the other way. What if I half the D, then I half the voltage? They are linearly but directly related. So in other words, one increases, so does the other, right? By the same factor, right? If one decreases, so does the other, and by the same factor. So a linear direct relationship. Okay. Now, we've kind of done a bit of the work here already. It's saying derive the equation to determine the electric field between the two plates using graphical analysis. So, electric field, hey, I've already kind of done that here, right? Equals change in V over change in D. Well, not quite done it, but getting there. So the potential difference over the separation distance, potential difference, did I just say distance? So if we want electric field, and that's the potential difference divided by the separation distance, then, hey, on this graph, that's a rise, right? The potential difference. And on this graph, that's our x variable, that's a run. So rise over run is slope. So for a graph where you plot potential difference as a function of separation distance between plates, the slope of that graph will give you the electric field magnitude. So H asks us to find, just for fun, derive the equation to graphically figure out the impulse of the ion. I'm going to add to that, okay, given time. So if we were given time. So the impulse, right, equation we have, let's just start here. Impulse equals F times the time interval. So the force exerted times the time interval, the change in momentum. Okay, now what is the force here? The electric force is what's actually acting. Okay, so F electric over Q equals the electric field. And so the electric force equals the electric field times Q, right? Newtons per coulomb times coulomb gives you newtons. That makes sense. Okay, so let's go plug that in. So the momentum, change in momentum equals electric field times charge times time. Okay, well, we already know this is the slope, but if we want to be really rigorous with it, which we always should, okay, equals, as we said before, the potential difference over, just replacing electric field with the expression for it here, times Q times the time interval. And so if we wanted the impulse, given time, we would do slope, okay, and multiply that by the charge and the time. Okay, so that wraps up the ion propulsion question. I know that's a lot, but it does kind of go through a lot of different concepts and put them together in a nice sort of